enable the instruments to warm up before we start any analysis. And this is just a way to enforce this. So we can set a warm-up time, and this essentially just locks our software down, prevents us from actually running any live analysis. We can still create our lab books, we can still look at data, process data, export data, but we just can't run anything. So it just forces us essentially to only use the instrument when it's ready and warmed up. When it's warmed up, we can say what measurement mode we want to essentially warm up in. So for example, here we've got it as the M, no AGD, no gas mode, and in a single quad mode, so it's a fairly basic mode. What we can also do is say once it has warmed up, we may want it to start in a different mode, so it gets sort of conditioned in that mode before we start our analysis. So after it's done its warm-up, and then we can set obviously the time of the warm-up, so it could be 10, 15 minutes maybe, or for ICPOES maybe even just as little as 5 minutes. We can then say what mode do we want to get ready in after. So maybe we're doing all our analysis in KD mode, so although we're warming up in no reaction gas or KD mode, we then want to change to KD mode to get ready for our sample analysis in this mode. So that's another layer we can add in. When we're doing these modes as well, we can set some instructions in our auto sampler. So where do we want the probe to go while we're warming up, after warm up, etc. as well. So we're conditioning in the right solution, so when we come to our instrument, it's in the state we want to find it. And the final thing is automating some procedures. So again, generally, after we've sort of warmed the instrument up, we want to run some performance checks. So let's automate these into our get ready procedure. So if we move the slider across here, what we can say here, we're doing a performance check in KD mode, because this is the mode we're going to do our analysis in. And then what we can also do as well is say, perform a auto tune if it fails. So rather than just saying running it, failing, and then we've got to do some manual actions to correct that, what we can say is if it fails, run an auto tune, and then it will repeat the performance report, and hopefully that's then passing after a tune. So hopefully once we've done all this, we've set the instrument to turn on, it's done all its checks, it's tuned if it needs to, and then when we come to the instrument, it is ready for us to start running our samples. What we can do is just press OK on this and it does it immediately. What we can also do is schedule it. So even we could set this up the night before and we could set a time. So actually when we come into the lab in the morning, it is again, it's in a state where it's ready and we can start our analysis immediately when we start our day's work. So as we can see, the get ready process provides a structured set of steps that reduces the risks of any missed tasks and supports consistent day-to-day performance.
So thanks, Matt, for showing us those nice features of Get Ready. Let's move on to look at the main structure of our analysis, which is creating our lab books. So you can start a lab book from scratch, or you can load a template.
Yeah, templates are quite useful, aren't they, if we've got set methods, so it saves us a bit of time when we're creating our lab books. And they can be particularly useful, actually, when we're integrating with LIMS or have a CSV sample list.
Yeah, so let's have a look at an example of how we can do that. So like we've said, templates are a really useful tool to automate some of our workflows every day. It saves us some time in the lab, and it just makes our labs that little bit easier. So I'm going to create a lab book now from a template that I've got. I've given it a name like you're probably familiar with, and the template here, which is our oils template, I've got 9 samples racked up, ready to go, and all I need to do is press create. And as it creates that lab book from my template, it's automatically going to pull through all those method parameters that I've got in here. So we're going to come back to those shortly in the webinar, and we'll just have a look at some tips and tricks on how we can get the most out of some of these tabs. But for now, looking at our sample list here, you can see I've got all my sample labels filled out, with the exception of the samples themselves, but the standards and the QCs. My rack and valve positions are put in here. So, for example, if every day you're using the same standards in the same positions in the rack, you can just keep them there, and you don't have to keep remembering to put the valve positions back in qtegra. It's also filled in my sample types for me and my standard types as well, which means that all the concentrations are being pulled through. I'm not wasting time typing out those concentrations again. And the same for these standards. So these standards, maybe they've got a shelf life of a couple of weeks, and we keep them in the fridge and then we bring them back out. I don't want to have to keep typing out all these weights every time. So I've got these built into my template as well. Now all I need to do is filter by sample type, which you can do using the little filter icon on any column, but I'm going to do sample type this time. Choose unknown, and I can fill in all my samples and my rack and bar positions as well. And anytime we've got cells in qtegra, we can highlight, drag those cells, right click, and we have the options to fill down if we want to fill down the same information, or increment fill on our rack and bar positions. And a handy little tip to know is if you've racked up maybe 2 or 3 racks and you do the increment fill, it will automatically change the rack as well if we highlight both columns together. Now, if you're in a position where you've got barcoded samples, for example, now, what you could do is just go through and scan those barcodes and fill in the sample labels and maybe even the amounts and the weights and the quantities in there as well, if you've got those. However, it might be that you've got a LIMS system that you're using and maybe you're exporting data from a CSV file and you want to use that information here. So what we can do at this point is we can either import it using the import button at the top, or we can go back to our lab book page and we can do it when we create our lab book. So if I tick the box here to import from CSV, you'll also see that I've got this little red icon here, invalid name. The name already exists. So anytime you try and do something in qtegra and it thinks it's wrong, it can't let you do that. So we just need to give this a different name. I've got my CSV file already selected and the mapping file. The mapping file is important. This tells the qtegra where those particular columns are in the CSV file and how they relate to the columns within qtegra. So I'm going to create that lab book. And this time, it's pulled in all the same data, but instead of having to go through and fill in all my sample names, they're already done. My rack and bar positions even I've got in here, so they're already done. And my amount, final quantity, weights are done as well, so I don't have to go back and add all those. So a nice, quick, simple way to save you some time every day, particularly if you've got a LIMS system and you want to integrate with qtegra. Yes, you can see that templates just really help us out every day in the lab, just automating our daily workflows, making life a lot easier. But to get to that stage, to have a nice method to use in our templates, we need to have validated and developed a really good, robust method.
Yeah, and part of that process is to make sure we've selected appropriate wavelengths or isotopes. And we need to take into account things like what interferences may be displaying themselves. So I'll show you now what tools we have in the software to help us with that thought process. So now let's have a look at the process of how we would go about selecting the wavelengths we want to use in our method and what tools are available to help us with this process. So let's have a look at magnesium, adding in magnesium to our method. So what we can do is just take the software's recommendation, but sometimes this is just the most intense wavelength, and this isn't always appropriate, particularly if this is quite sensitive and we're looking at a fairly wide range, wide concentration range. So let's have a look at potentially looking at different wavelengths. So first of all, we get a table where we can see all the different wavelengths and their intensities, so generally they're going down in intensities, but again, we may want to know what interferences are going to be present as well, particularly if we've got a bit of knowledge about what else is present in our samples. So we can expand this up and have a look at our wavelength tables, our interference tables. So we can see our first wavelength, our recommended wavelength for magnesium is pretty clean, not much interference going on here, and it's pretty intense. Same with the next one and even the third one down, so we've got a good choice of wavelengths here. But it may be, like I say, these are too intense for the wavelength range that the concentration range that we're looking at. Let's have a look at the next one down, magnesium 202 nanometers. So we can see we've got a lot more interference going on here. Now this may be appropriate for the intensity, for the concentrations we're interested in, but let's say we've got loads of cobalt in our sample, so we can see this there is a fairly pronounced interference or spectral overlap caused by cobalt on magnesium. So if we do have cobalt in our sample and we're looking to measure magnesium, then again, this is probably not going to be the best wavelength to use. So we can take this process with any other element we're looking to add to our method. And like I say, based on some information we have in our sample, whether we know that already or whether we use some additional tools like semi-quant to get that information, then we can obviously make some good educated guesses on the wavelengths we want to use in our method. So let's just add in the first 3 magnesium wavelengths and go to our next page, the acquisition parameters, and just see what other information we can get. So maybe that we're looking really low level, so obviously these are going to be very good, they're nice and sensitive. How do we increase our sensitivity further, or how do we increase the limits of detection we can achieve? So we also can say what exposure time we want to use. This may be limited to the instrument you have, but typically if we increase this exposure time, we increase the achievable limits of detection. So 5 would be, for this particular model, the lowest we can go down to, but it may be that we want to increase this to 10 seconds, maybe even 15 seconds, to get some improvements in the limits of detection we require. Let's now look at the ICP-MS and go through a similar process. So what we're going to do here is take a couple of examples. So the software here will make some recommendations. Unlike the OES, where it's just adding in the most intense, now this will take into more considerations into some of the interferences that are present. So for example, if I select molybdenum, and then we look at the isotope it's chosen. So it's chosen mass 95. Now this isn't the most abundant isotope of molybdenum. So why has it chosen this? If we look at the most abundant isotope of molybdenum, mass 98, we can see we have an isobaric ruthenium interference. So that is why this has not been automatically selected and it's chosen mass 95 instead. Now, again, looking at a similar thought process, if we have some knowledge of what's in our samples, again, maybe this is not the most appropriate. So again, we've got this big argon manganese interference here on the default isotope. So again, if we know we've got a lot of manganese in our sample, again, maybe this is not the most appropriate wavelength, or sorry, isotope to choose in this case. We also have, if we're using a MTX or a triple quadrupole ICP-MS, we have inbuilt reaction finder, which helps us to select what modes to use, what reaction modes, and whether we're looking at product ions or measuring that isotope en masse. Let's have a look at an example of this using arsenic. So I've just used the default arsenic. And again, if we go into our acquisition parameters, we can see the software has automatically selected arsenic to be measured in O2 triple quadrupole mode and measuring arsenic at its product ion of arsenic oxide, a mass 91. So we've not had to do anything there. Don't necessarily need that chemistry knowledge to determine whether arsenic reacts with oxygen or it doesn't. The software's done all that for us. So it's for the molybdenum, it's automatically put that in KD mode. But again, we do have the option, the flexibility to change that should we wish. So let's say we want to put everything in the same mode. So we also want to run this in triple quadrupole mode and oxygen mode. Now this is not the default, so the software hasn't proposed this for us, but again it does give us some idea whether we want to measure it en masse or by mass shift. So again, if we look at the Q3 analyte, we can see there's a default one here. So this says to us that the software is telling us molybdenum reacts with oxygen, so we should be measuring Q3 molybdenum oxide. So then we can just select that and we know that this is going to give us good data. Typically when we're running ICP-MS, we want to be running some internal standards as well to help with the accuracy of our data. But again, what internal standards should we use? Again, if we're using reaction modes, the internal standards may behave slightly differently than we assume. So what we can do is right-click, and again, the software has got some nice features that give us some options of internal standard analyte that we've selected. So for arsenic, for example, we may want to choose germanium, and then it automatically puts that in the right mode, TQO2 mode. This time it's measuring it en masse. So it's telling us that germanium doesn't react with oxygen, and now we've got a good internal standard to correct our analytes of interest. In the same way we changed the exposure time for the ICP OES to get better limits of detection, we can do the same with the dwell times here. So if we want to get some better detection sensitivity, then we can increase these dwell times as required.
So Matt's shown us some really useful tools there that we can use for our method development and to have a look at how interferences might be affecting our analysis. Sometimes we've no idea what's in our sample. They're brand new samples that we're doing method development with. So we've actually got some nice built-in tools that help us do maybe some survey scan or semi-quant of our samples so that we can see what else might be there. So I've opened up the semi-quant tab on our ICPippo, and as the name suggests, this is a semi-quantitative analysis feature that we've got built in that lets us look for all these elements you can see here in our sample, and it just gives us a rough idea of what might be in our sample, which is useful for looking for some of those interferences Matt showed us before. We previously ran a whole webinar looking at this semi-quant feature, how to run it and how it works. It's automatic, it's out of the box. So if you're interested in this, then please have a look at that webinar where we go into a lot more detail covering that. Skipping over to the ICAP MTX that we've got here, the lab book, we've got our survey scan tab. Now what this does is this can scan a full mass range for us. In this case, we've got this set up to scan between 6 and 250 units there, atomic units, and it will scan that full mass range. And again, it gives us an idea of the intensities of elements that might be in there. You can see we've got, for example, this protected region at mass 40. That's because obviously we've got lots of argon in there at mass 40 for our auxiliary gas and our cooling gas and our neb gas flows. And we're going to take a deep dive into this in our part 2 webinar where we'll look at the results. We'll show you some survey scan data so you can have a look for yourselves. So I've skipped ahead to our intelligent uptake and rinse tab here within our method. And this is quite useful sometimes if we've got some tricky elements we're having particular uptake or rinse problems with. So one common example is mercury. So mercury is quite sticky. It gets in our line, in all the lines and the tubings, and maybe we want to have a good washout of that. Now, what's important to know is that what we need to do is get the chemistry right first. So before we're resorting to using our intelligent rinse system, we want to look at other ways of being able to do that. So for example, for mercury, that might be adding some hydrochloric acid. For other elements, it might just be maybe bumping up from 1% nitric to 2% nitric in our rinse, and just getting the chemistry a little bit better and getting the washout better. We've also got our auto sampler options. We can just increase our uptake time, or we could also use something like step ahead or use a valve-based system to improve our washouts as well. If all of those options aren't working, then this is when we can come to our intelligent rinse here. So if I toggle it on within my lab book, we've got some settings here, minimum and maximum delay. So what it's going to do is it's going to firstly wash for at least that 30 seconds and up to 300 seconds, so 5 minutes. So in the example of mercury, you can see I've searched for mercury down the right-hand side. I'm going to drag that in here. It's going to do my wash for 30 seconds. It's then going to wait until my signal gets below the number of counts I've got in here. So the instrument will monitor that. And again, I can set a dwell time for that. I can set this to maybe something like 200 counts, 100 counts, depends on what your analysis is and what you're doing. And then for up to 5 minutes. And after 5 minutes, it will then trigger the failure action. So I can either abort that lab book or abort the queue and say, actually, the system isn't appropriate for use. We're going to wash it out a little bit more. Or we can just ignore and continue on to our next one. But like I say, what we want to do is we want to get our rinses right in the first place so we don't have to resort to this intelligent rinse. We can do something similar with intelligent uptake. It does exactly the same thing, but during the uptake time, it's going to monitor the stability. So you see we've got the column for signal above rather than signal below, and then we've got a stability option as well. So what is our sort of percent relative standard deviation on replicates? So moving on to our interference corrections, like Matt said, sometimes we do get these interferences, and often we might opt to switch wavelength or switch mass, depending on whether we're on optical or MS. But in some cases, there might just be no way around it, no alternative wavelength or no alternative mass. So we need to account for it with an equation. And we can put those equations into our interference correction page. So if I just go back to my analytes and I choose a mass such as indium, which the default is 115 there. When I go back onto my interference correction page, you can see actually that down the left-hand side, all my elements are here, and the indium is showing that there is actually an interference from tin. So we can account for that interference with the equation. And qtegra knows some of these interferences and it knows some of these equations. So you don't have to research them, you don't have to manually type them in. So if I click and drag that into qtegra, you can see that it's put indium in our mode here, M off KD, single quad mode. It's got the correction factor, but it's missing the tin. And that's because we've not added that mass of tin at 118 into our method already. But if we just press the little magic wand here, it adds in the missing analyte, 118 tin, and it puts it in the correct mode for us. So if I go back to our acquisition parameters page, you can see it's added tin in and it's put it in the same mode to match our indium. We can also use the interference correction page in another way. So one example is summing isotopes together. So for elements such as lead, we often find that the abundances can be different depending on where the sample comes from. So this is often important in geological samples, where we might have a different isotopic ratio of lead in one sample and to another sample that's come from somewhere else in the world. So if we look at our lead isotopes, our main ones are 6, 7 and 8. So 206, 207, 208. I'm going to select all three. Now what that does is adds them into our acquisition parameters page, and you can see we've got them here, 206, 207 and 208 lead. But I want to add them all together so that we've got a representative for every sample that we run. Go back into my interference correction equation page, we can add them in here. So if I drag 208 onto my page, it adds a new line with a blank formula. I want to add 206 and 207 as well. So if I drag 206 over the top, where the little green plus icon is, you see it adds the equation in, and I'm going to add 207 over the next plus. So what it's going to do now is report on the 208 line, also added into it the 206 plus the 207. So we get them all added together, and I don't have to do that manually myself offline afterwards. So here I am in the standards tab, and as I alluded to earlier, when we create a template, we pull in all those standards from this standard tab. We don't have to type them out every single time. So once we've put them in once, we're sort of done. And in this case, we've got a bunch of standards, we've got a couple of QCs, and as you can see, if I click through them, we've got multiple elements, all sorts of different concentrations. So this would take a really long time for you to go in and have to type them out every time. So what we can do is we can save these within qtegra globally. So if I click, drag all of these, and right click, we've got this option to pass to global. And when we do that, it saves them within qtegra globally. And we can see what we've got in our global configurator by going into the configurator. Here we have all of our standards that are in here. Out of the box, we also get some of the NIST standards as well within there. So again, it saves you having to dig out the certificate and type those in manually. So if we want to add a standard from the configurator, we can just press this little open button and we can add them one at once. Or we can select multiple, same way again, click and drag like we did before, click OK, and it adds those standards straight into our lab book here. If you want to do maybe copy a standard, and we're doing our standards for serial dilutions, rather than having to type them out each time as well, we can right-click a standard, click copy, and we can add our dilution factor in here. So if we type a dilution factor in and press OK, it creates a copy of our standard, and it applies that dilution factor to it as well. Just saves us a little bit of time when we're setting up our lab books or our templates.
Following on from the Standards tab, we have quantification. And here we can do several tasks, such as defining our internal standard and assigning it to our analytes. And we can also set some instructions on our calibrations. So for example, the fit type and any weighting or forcing that we want to do. Another task that we can do here, which is particularly useful, is setting a standard range and switch point. Now, why would we want to do this? It could be that we're looking at quite a wide calibration range, and as a result, we need to use a low sensitivity wavelength, and ultimately then we're sacrificing a bit of sensitivity. But there is a way in which we can use multiple wavelengths and use some sensitive wavelengths up to a certain concentration to achieve good sensitivity and limits of detection, and then switch to a less sensitive wavelength at a certain concentration to maintain our linearity up to the range we require. Now here we're going to have a look at a little bit of data just to help us explain how we go about setting this up. So we've got a method here where we're looking at calcium, potassium, magnesium and sodium, but I've just cut the data down just so we can look at a couple of calcium wavelengths and we're going to set it up on this. So we can see we've got two calcium wavelengths, one really sensitive, so calcium 393, and we can see it's too sensitive for our calibration range of 200 milligram per litre. You can see we've got this very, very curved calibration. And our less sensitive line, calcium 317, we've got nice linearity over this range, but maybe not as good limit of detection. So first of all, we need to establish how or where does our linearity for our sensitive wavelength fail. So to this, we can just keep removing some of the top standards and keep doing this until we essentially achieve linearity. So we can see at the moment it's pretty poor, the R-square is pretty poor, so let's start removing some of these calibrations. We can see it's getting a bit better. Let's keep removing them, and okay, not too bad, but let's see if removing the 20 milligram per litre. Okay, so this has given us up to 10 ppm, perfect linearity. So we can see this wavelength is good up to 10 milligram per litre, but above that, it's too sensitive. So this would then essentially be our switch point. So let's go back to quantification and set this up. 393. So we know that this is good in the range 0 to 10 ppm with a switch point of 10. We're then going to use 317, so our less sensitive one, from 10 up to 200. Okay, so now we can say if we have a sample that falls within these different ranges, it knows which wavelength to use. What we can also do to help this is set up a combined one, so what we call a customized trace. So if we highlight the ones we're interested in, right click, add a multi-calibration customized trace, and it adds this calcium multi-calibration trace here. And what this also does is, if we go back to concentrations, it adds another tab here, and essentially we can see it's blanked out the concentrations we're not using, and we can see the multi-calibration trace. So when we look at a value here, for example, that's above our switch point of 10, 21.5, we can see it's taken it from 317, and when we've got our very low ones, for example 0.035 or 0.003, it's taken it from our nice sensitive 393. So we can see by combining the two, we've got excellent sensitivity, low limits of detection, as well as achieving nice linearity up to high concentrations.
So the last thing we're going to show you today is just a nice little tool that's hidden away and you may not have seen before. So at the bottom of your lab book on the left-hand side here, you've got this tab for settings, and if we expand it, we have this little section here called limits. So these are limit sets that we can set up in here. So what I'm going to do now is show you how we set up those limit sets, and then in our next webinar we will have a look at how that affects our data. So we can create multiple limit sets, and these will flag data that are above or below certain criteria that we set. So we can add new limit sets and have different limit sets for different sample types to apply them in there. So if I create a new limit set, for example, and this is going to be for my diesel samples. Create that limit set, and you can see in the drop down we've got a couple of different sets now in there. And I can create a high limit or a low limit set, and by ticking them you see it ungrays these boxes. So in the low limit section you can see I can get it to flag anything that is maybe below our detection limit, LOD, anything that's below the minimum quantifiable level, or a user-defined number. So if, let's say, you validated some limits, you can put those in here. So let's say I want to flag anything that is below 0.5 ppm in there. And as we looked at earlier, anywhere you've got a cell in qtegra, click and drag, right click, you've got the fill down option as well. So we can put those in there. And it's the same for our high limit. We can either say flag anything that is over our calibration range, because maybe we need to do a dilution on that sample, or again, a user-defined limit. I'm going to do calibration range for these ones and fill those down. And then the last thing we need to do is to say, What do we want that to look like? So if we click next to the low limit format here, we can say anything that is below our criteria we've defined, we want to show up a certain color. Maybe that's something like orange or in bold. Or we could even add some text. So we can add text to display to the left or right of the value, or even just replace the text, the number entirely with text. So I'm going to say, let's replace it this time with less than LOD. So now anything in my data will be flagged as less than LOD. My calibration range, I'm going to set those as well. I'm going to say, set a nice dark blue. And again, I'm going to set those bold, but I don't want to replace the text because I want to see the number, because then I know what level dilution I need to do. So now we've set up our limit set. Back into our sample definition here, because I'm in a template, I can apply that limit set. So for example, on my sample line here, I can apply that limit set here, and it will apply just that limit set to any samples that are replicated from creating this template.
So that brings us to the end of part 1 of our qtegra tips and tricks webinar. So today we've covered the dashboard, the get ready workflows, and we've looked at some tips and tricks on how to build your lab book from start to finish and how this can improve your daily lab efficiency.
And then in part 2, we're going to move on to what happens after the analysis. So we'll look at things like intensities, calibration tools, recoveries, readbacks, flags, and exporting our data back into a format that maybe we can read it in our LIMS system, as well as looking at putting into practice some of the tips that we've discussed with you today.
Hopefully you've been putting some of your questions in the Q&A widget. If not, there's still time to do so. So now we'll move over to our live Q&A session.
So yeah, just lastly to say thank you for joining us today, and we look forward to seeing you again in April, where we'll have our second episode of our Lunch and Learn webinar series, and this will be our part 2 qtegra tips and tricks.
Hello and a warm welcome from Germany and the UK. My name is Petra Gerhards. I'm the Regional Marketing Manager in EMEA for GC, GCMS and Trace Elemental. And I would like to welcome my colleagues David Fischweg and Matthew Gregory. Thank you so much for this really interesting presentation on qtegra. And obviously, we have a couple of questions already. So let's start with the first question. We are currently creating new lab books from scratch for each analysis, or by creating copies. Are we okay to do this, or is it better to use templates?
Yeah, okay. So you can absolutely build your lab books from scratch or from copying existing lab books. And in smaller labs, this might work fine initially, particularly for method development or if you're doing some validation. The risk comes when you're creating copies of copies over time. So small unintended changes might creep in, or in some cases, you could get corruption of your lab book structure. So our recommendation is maybe use your lab books from scratch when you're doing your method development, your validation. But once you've got to that stage where you know what your method is going to be, then we would say let's create some templates. This gives you a clean master version that everybody in your lab can work from, so everyone's working from the same version. And this improves consistency across users between days. And if you're in an accredited laboratory or a GXP environment, we can lock these down as well. There's no differences between different analyses. They also allow you to build in automation as well. So things like creating your lab book from the template means we can have standard and blanks at the beginning. Maybe we could have repeated QCs inserted at defined intervals. Let's say we need to run one every 10 samples. We could put that in as part of our template definition. We can put in our pre-configured dilutions. So if we're always doing the same dilutions for the same types of sample analysis, we can put those into our template. And then we can also automate CSV exports and reports as well into a folder for LIMS and things like that. So there are benefits to doing it. for running those templates. So we would always say, try and run those templates if you can.
Thank you very much. Next question. How often would you recommend running an auto-tune on the ICPMS? We are currently doing it daily before each method.
Yeah, okay, I can take this one. So I would say, yeah, you can auto-tune every day, although maybe not necessarily essential. So obviously if you tune every day, you're kind of making sure your system is in optimal condition. But really, we would recommend running performance reports every day. So as long as your performance reports are passing, I wouldn't necessarily say that you need to do the tuning. One time we would absolutely have to do the tunings if we did any maintenance. So if we're taking the system apart, cleaning the cones, cleaning the sample instruction system, then yes, definitely we'd do some tuning, but we don't necessarily have to do it outside of that. We'll talk a bit more about tuning and interpreting performance reports and when and why we might do tuning in the next webinar, actually. So if you tune back into that, you'll get a bit more information there.
Thank you. In qtegra for ICAP 7000, it was an option to do auto peak from the method, which was very useful because we do not need to select all wavelengths again. You want to say something about this? Was that not a real question? Is this just a starting point?
That's fine. I think I think David's having maybe some problems with his microphone. So this is a question about the auto peak. Is it?
Yes. About the auto peak from the method, which was very useful because we do not need to select all wavelengths again.
Yeah, no, that's fine. So yeah, it slightly changed how we do the auto peak in the Pro software. So we've taken it more global. So David did a bit of a demonstration on the modes and the tune sets. So now the auto peak is specific to a tune set. So really the first time you use a particular wavelength in a tune set, we auto peak it, and then we don't really need to do it thereafter. So if we're setting up another lab book using the same mode or tune set and the same wavelength, we don't need to auto peak that wavelength. If we're using a new wavelength, or it's the first time we've used that wavelength using that tune set, then yeah, we can auto peak it, but outside of that, we don't need to. So it actually, in a way, should be a bit more efficient than the ICAP 7000, because every time you create a new lab book, you had to do the auto peak, whereas now, if you're using the same wavelength and the same mode, even if you create a new lab book, you don't need to do that auto peak. The information should be carried through because it's a global parameter now.
Thank you very much. I guess that answered the other question as well. So I have an ICAP OES. I can sort the analytes of interest alphabetically, and it saves that order with the corresponding icon. But when I'm reprocessing data, that order disappears whenever I make a change to the sample list. For example, to remove a calibration standard. The alphabetical order disappears for both concentrations and intensities. I've already tried different method configurations, but none of them work. Do you have an answer for that one?
Okay, yeah. So obviously we can sort through, maybe there is some, as you make changes, it does reorder, but there should be a button next to the ordering which saves that order, so we can do that. If you're still having problems even using that save, what we probably want to try and do is save that within the template. So get the order right first, save it in the template, and then it should be okay going forward if we click the button that's next to the sorting that says keep this ordering. Hopefully that will work.
Okay. Is there an opportunity of making my ICAP Pro ICPOES even faster than 3 minutes for each sample?
Okay, so I would probably say that 3 minutes per sample is pretty slow, depending on how many modes you're using, what exposure times. But you know, if we set it up in a certain way, we can easily get below 1 minute a sample. That's, you know, we could use a combination of fast uptake and rinse. We can use the step ahead functionality of the ISE65 auto sampler if that's what we're using. And there's no reason why if we're using maybe one mode, so to less than 1 minute sample. If we're then using multiple modes, if we're using axial and radial, then it may go up a little bit. Again, if we're using longer exposure times, it may go up even more. But really, yeah, we should be able to get less than 3 minutes a sample, definitely. Again, different models have different minimum exposure times. So I think that the example David showed today was minimum of 5 seconds. So some of the maybe lower end models have a slightly longer minimum exposure time, so they will be slightly slower. But yeah, you should be able to get it quicker than 3 minutes, definitely.
Thank you. How to add a custom column in qtegra?
Okay, yeah, so there is a way of doing that, probably a bit difficult to explain over a call like this, but I can see who submitted this question. So Harry, I think I might have a document that explains how to do this, so I can certainly share that. I can certainly share that with you offline and explain how to do that.
Thank you. I understand that there is a second part of this webinar. If registration is open, okay, I can say something to this because I set it up. We can already send you a link, but there will be also an official invite. Before the webinar, there will be an official email going out. But what we can do is, obviously, we already have the links for all the webinars this year. What we can do is we can send that to you separately. So coming to the next question. In blank water itself, my nickel iron counts is more than 10,000. I changed the tubings, cone, nebulizer, but still my counts were high.
Okay, probably quite difficult to answer without a bit more sort of context, but it could be contamination. So it could be in the water itself. So iron, I know, is quite easy to contaminate with. So it could be some iron water. You could try just aspirating air through the system. Do the counts change when you have air going? Is it, then you can identify, is it in your system or is it in the water itself? Yeah, I mean, it's quite difficult to identify, but I know iron is very easy to contaminate with. Elements like iron, aluminium, zinc, quite easy to contaminate. So it possibly is just a contamination issue. Yeah, I would suggest that if you've changed everything, cleaned everything, it probably is just in the water itself.
There is another question related to this, and maybe that is something that you would like to take offline and discuss directly with the customer.
Yeah. Again, I can see who it is, so I can reach out to them directly to expand on this.
Thank you for doing this. When setting a calibration, how do you decide on the best fit type and whether to apply weighting?
Okay. So, I mean, generally, we want to have a linear calibration. So that's our ideal situation. We want to set everything to linear where we can. Sometimes, if we have a particularly wide range, what can happen is we can get some sort of heavier weighting towards the top end, and we see a lot of inaccuracy at the bottom end. So in these situations, maybe 1 over concentration or 1 over concentration squared will give us some better accuracy at the bottom end. That would be my sort of two things. Linear where you can, but if the range is wide, then maybe consider 1/over concentration.
Thank you. We usually report 2 decimal places and so are manually rounding results down. Is there a way to deal with this in qtegra?
Yes, yeah, absolutely. So within qtegra, if you're in the concentrations page, there is a cog at the bottom, which essentially means the settings. So you can change various different accuracy, so how many decimal places for any of the settings really, so the concentrations, the intensities, the R squared, the LOD, things like that. So you can just change them within the lab book there. If it's a parameter that you want to change for everything, then you're probably better off doing that within the configurator software, and then it changes that globally. So you don't have to keep changing it in every lab book. You can change it, in the configurator, then it changes it thereafter. So that's in the evaluation parameters in the configurator.
Okay. I don't know if this is possible to answer right now or if you have to take this offline with the customer. I have a TQ ICPMS. When I use the internal standard, I have a result, a high percentage, about 90,000%. I don't know why. Is that something that you can answer now that you would like?
Yeah, possibly. Well, there's a couple of reasons why it might be going that high. So one reason, so everything is referenced to the blank. So your blank should be called 100%, and then everything relative to that is what it is. So it could be that you have no internal standard in your blank. I don't know if you're spiking it in or adding it online, but if there's no internal standard in your blank, that calls it 0. Then if you have high counts, it's going to call it, say, ridiculously high numbers like 90,000, for example. So it could be something like that, or it could be the presence of that internal standard in your sample. So if you're using yttrium, for example, as an internal standard, but your sample has loads of yttrium in it, then it's obviously going to give you a really big false positive. It's usually a reason behind it. So yeah, I think they're probably the most likely reasons. There's some sort of interference going on, or there's nothing in the blank and it's giving a false positive like that.
Okay, I come to the last question. You can still answer questions, or you can still put questions into the chat and we will come back later to it. But in the interest of time, because we are running over 1 hour, this will be the last question that we are going to answer live. What would be an optimal exposure time for measurement that is measuring 30 elements at a time? We have up to 600 samples a day, so it would be very nice to go from 3 minutes near to 2 or even 1 minute of measuring time for each sample.
Okay, so I assume we're talking about an ICP OES here. So in reality, it doesn't really matter how many elements you have. It's a simultaneous system. So whether you're running 1 element or 30 elements, the time is the same. Again, it depends kind of what limits of detection you're looking for and what instrument you're using. So if you've got an ICAP Pro XP and you can go down to 5 seconds, then 5 seconds exposure time won't give us the absolute best limits of detection, but it gives us pretty decent data. So if that's workable and if that gives you the limits of detection you need, then 5 seconds is fine. And again, like I answered with the other questions, then if we couple that with fast uptake and rinse, maybe step ahead. If we have access to it, then we should be able to get you down to less than 3 minutes, no problem.
Thank you very much. So again, if you still have questions, you can put them in the chat and we will come back to it later over the course of the next couple of days. A link for this webinar will be sent to you within the next 24 hours if you would like to share it. We have a second qtegra webinar that is coming up in April. And we are going to send out invites, but if you're interested, just contact David, myself, or Matthew, and we can already provide those links. With that one, I would like to thank the customers for attending this webinar, and I also would like to thank David and Matthew for the really nice presentation and also for answering the questions. Thank you very much and have a nice day.
Yeah, bye-bye.